Okay, so let's start off our lecture here on continuing in section 6.5, evaluating the definite integral. Last time we looked at how to evaluate the definite integral, and I gave you a couple of exercises to work at home. So we did 5, 7, 15, 25, 33, and 45. So we'll kind of work through those. And then after that, we're going to go through a couple more just exercises involving the properties with the definite integral. So we'll start off with exercise 5. And okay. Make sure to keep an eye also on the chat window. If you have questions, feel free to type something in there. And I also have my email open as well, so I'll try to keep an eye on everything. So we're going to integrate from 0 to 2 x squared of x cubed plus 1 all to the 3 halves dx. So what I'm going to do then is solve it for the indefinite version first, and then we'll plug it back into the definite version. So integrating that first, I have x squared, so I'm just going to write that again. X squared times x cubed plus 1 all to the 3 halves dx. And this is a integration problem that we'll have to use with substitution. So we let u equal x cubed plus 1, and when we differentiate that, I get 3x squared dx. And again, just let me rearrange this a little better. So this part right here, we would replace this with u 3 halves, and this part here is what I'd like to be able to replace this with du, but I have a 3 still here. I have 3x squared dx, so I'll bring the 3 over to the left hand side. So I have 1/3 du equals x squared dx, and that means that I can replace that with 1/3 du. So I got u 3 halves times 1/3 times du, and with the property of the integral, I can bring that 1/3 in front because it's just a constant. And now I can actually integrate here. So I have u 3 halves, so that goes up by 1. So 3 halves plus 1 is 5 halves. And in front, it becomes 1 over 5 halves, or, to simplify that, 2 over 5 plus c. So again, right here, that's the 3 halves plus 1, or 3 halves plus 2 over 2, which gives me 5 halves. And in over here, that's 1 over 5 halves, or that again simplifies down to just 5 on the bottom, and I can bring that 2 up top. So I'm left with 2/15 u to the 5 half plus a constant, and I'm not done yet because I need to substitute back in my u. So I got 2 over 15 times x squared, or x cubed plus 1 all to the 5 halves plus a constant. So now I can actually solve the definite integral of this. So we know what the antiderivative of that is now. It's 2/15 times x cubed plus 1 to the 5/2. We don't have to worry about the constant of integration, because we're using a definite integral, and the limit is from 0 to 2. And now we substitute our values in 2 and 0. So it's the antiderivative evaluated at 2 minus the antiderivative evaluated at 0. So 2/15 times 2 cubed plus 1 all to the 5/2. And now I need to subtract the antiderivative at 0, which is 2/15 at 0 cubed plus 1 all to the 5/2. And now the rest is just arithmetic. 2 cubed is 8 plus 1 to the 5/2 over 1 to the 5/2. So that is still 2/15. I have 9 to the 5/2. 2/15. Okay. This is when I'm going to pull out a calculator. 9 to the 5th is 59,049. And taking the square root, I get 243. And multiplying that by 2 gives me 486 divided by 15 over 2/15, which leaves me with 484 over 15. Why is it 2/5 again in front of you? Okay, hopefully I answered that right here. Is that okay? Okay, perfect. Yeah, and you can also think of that as, that's also equal to 1 over 5 times 2 to the minus 1. And to get rid of that negative exponent, you just bring it up into the numerator. So okay, so the final answer that I got was 484 over 15. And in the back of the book, they give 19 over 15. And I'm not sure how they got that. And I double checked that. So this one is correct. So hopefully that's what you got. It was 484 over 15, and if you got the answer in the back of the book, which was 19 over 15, it's wrong. I'd like to know how you got it, because maybe they made the same error when they were doing the answer at the back of the book as well. Yes, okay. Why is it 1 over? Sure, we can just answer that in just a second. Let me just push this up. So for our power rule of integration, it's the integral of x to the n dx is equal to 1 over n plus 1 times x to the n plus 1 plus a constant, and this is assuming that x is not equal to 0. Oh, sorry. This is assuming that n is not equal to minus 1. Right, because when we have minus 1, that becomes x to minus 1 dx, which is equal to 1 over x dx, and we have a special rule for that, which is ln absolute of x plus a constant. Okay, so if you notice here, this is our rule. So let's say I have u to the 5 halves du, and so, oh sorry, let's go, it's 3 halves. So if I have u to the 3 halves, I have to, this is my n, and my n is 3 halves, and I have to add 1 to that. So that's why I have to do that. I have the 3 half plus 1, which equals 3 halves plus 2 over 2 to give me 5 halves. Okay, so that is my n plus 1. And I also have to have it in the denominator here in front as the fraction. So I also have to have 1 over 5 halves. And then that's where we can simplify that. So the 1 over 5 halves gives me 2 over 5 u 5 halves plus a constant. Just checking to see if everyone else is following along in the chat. If that's okay. Is that good? Okay. Okay, perfect. So then I will move on to the next one, which was number 7. Okay, so for number 7 again, we have the integral from 0 to 1 of 1 over the square root of 2x plus 1 dx. And this is a little bit complex again, so what we're going to use is substitution rule, and I'm going to do the indefinite first. So letting u equal what's inside of this square root here, I have 2x plus 1, and that's easy to differentiate. That's just x dx. Oh, no. Just dx. So I got to take the the derivative of 2x, and that is 2. So let me just write that a little bit clearer. So that is 2 dx. Now I'd like to be able to isolate that, so I want to be able to replace dx with something, so I'm going to bring the 2 over to the left hand side. So I have 1/2 du equals dx. So that means that I can replace 1 over the square root here. Instead of writing 2x plus 1, I'm going to replace it with u. And instead of writing the dx, I'm going to replace it with 1/2 du. And again, I can bring out that 1/2 in front so that I have 1 over the square root of u du. And rewriting it so that I have negative 1/2 du. And now when I'm going to integrate that, I have to increase this exponent by 1, so that's minus 1/2 plus 1 is equal to positive 1/2. Which then means that in the denominator, using my rule, it's also 1 over 1/2. So again, 1 over 1/2, you can write that as you leave the 1 in the denominator, and the 2 comes up into the numerator, so I'm left with is equal to 2 over 1, which is equal to 2. So I'm left with 1/2 times 2u to the 1/2 plus a constant. 1/2 times 2 cancels, so I'm left with u to the 1/2 plus a constant. Or you could also rewrite that as the square root of u plus c. And substituting in what u is, I get the square root of 2x plus 1 plus a constant. So then when I integrate it from 0 to 1, that's equal to, so I have my antiderivative, which is the square root of 2x plus 1. And here's my limits from 0 to 1. And now I substitute in the 1 into that antiderivative. Subtract that from the bottom one, which is 2 times 0 plus 1. And I'm left with 2 plus 1 minus 1, square root of 1. So I get the square root of 3 minus square root of 1 is 1. And there's my final answer, is the square root of 3 minus 1. And that's correct. That matches in the back of the book. Okay. Let's do 15. Okay, what did I write? What was the question for 15? Okay. Yeah. Okay, for 15, again, we're integrating the definite integral. So I got from 0 to 2, x times e to the x squared dx. Okay, again, we have to do a substitution on that. So the integral from x e, I'm just copying this again. And I'm going to pick x squared, because when I differentiate that, I get 2x dx. So this can easily get replaced with e to the u, and I'd like to replace that something with dx. But again, my du is not equal to x times dx. It's at this point is equal to 2x dx. But again, bringing that over to the other side, I have 1/2 du is equal to x dx. So I can replace that again. So there's my integral. I have e to the u times 1/2 times du. And I can bring the 1/2 in front. And the integral of e to the u is e to the u, so I can leave that alone, plus the constant. And now that I'm done integrating that, I can replace the u with what it was originally. So it's 1/2 e to the x squared plus a constant. Okay, so now I can put my antiderivative. So again, it's the antiderivative at 2 minus the antiderivative at 0. So it's, let me just write that down. The antiderivative is 1/2 e to the x squared from 0 to 2. And it's evaluated at the top limit. So 1/2 e to the 2 squared minus 1/2 e to the 0 squared. So 2 squared gives me the 4, so I have 1/2 e to the 4th minus 1/2 e to the 0. E to 0 is 1. So I have this. And then I can factor out the 1/2, so I'm left with 1/2 times e to the 4th minus 1. And so that's it. Just a second. Okay. Okay, and we're done for 15. Is there any question? Oh, yes. Prove Rolle's theorem. Okay. Usually anytime you start to use like specific functions to prove statements about calculus, it's starting to sound like you are using an example, and it doesn't necessarily prove anything from then. So, okay, moving on. Are we always looking to factor out anything possible when we provide our answers? And I have no idea what that was with our well-endowed observer. Exactly. That's just me. I was factoring it out because that was what was given in the back of the book. So I was just following that along. So 1/2, yeah. I saw that there's a half and a half here, and I just factor it out. And that's what matches in the back of the book, so good enough for me. You know, sometimes, like, if we're trying to look, yeah, that makes sense. Yeah, I mean, times when you start to factor things is when you need to start to set equations equal to 0. You know, when we were setting derivatives equal to 0 to find where the critical numbers were. That's a good time to start to factor things, and so we can quickly find what the zeros are of that function. But in this case, it's not necessary to really factor that out. I mean, this is still simplification to this point, but basically these were things that we could easily manipulate. Okay, and then we did 25. I said to do, these were our at-home exercises. So 25 is the next one that we were going to do. And that was the integral from 1 to 2 of 4 times e to the 2u minus 1 over u du. And I'm going to break this up a little bit just using our rules of our properties of the definite integral. So I'm going to break that up. I'm going to go from 1 to 2 of 4e to the 2u du, and then I'll do the minus from 1 to 2, 1 over u du. So again, I'm just applying the integral to each individual function that's of the difference here. Okay, so this one is fairly easy to calculate because 1 over u is one of our rules. It's ln x. The more difficult one is this one right here, the integral of 4e to the 2u du. And they're being sneaky at this point because they've used our u's. That's what we usually use for our substitution. So, oh, you let w equal 2u. And then if I differentiate that, I get dw is equal to 2 du. And I'll bring that over to the left-hand side here, so I get 1/2 dw equals du. Okay, so I'll factor out this 4 here. I have the integral from the integral of e to the 2u du. And now I can replace that, so I have e to the w. And for the du, that's equal to 1/2 dw. And I'm going to pull out that 1/2 in front again, so I got 4 times 1/2 times the integral of e to the w dw. 4 times a half gives me 2. And then the integral of EW is EW plus a constant. And I'm not finished yet because I have to substitute what W is in. So in this case, it was e to the 2u plus a constant. So now I can actually substitute this back in. So the antiderivative of 4e to the 2u is 2 e to the 2u from 1 to 2 minus ln of, well, it's not x, it's u, from 1 to 2. Okay, and then I substitute in my values of 2 and 1, so I have 2 times e to the 2 times 2 minus 2 e to the 2 times 1. Now I have a minus. I have to be careful because I have a minus in front here and I still have to kind of subtract. So I have ln 2 minus ln 1, and ln 1 is 0, so I'm left with 2 times e to the 4th minus 2 e to the 2 minus ln 2, and then the minus times a minus would be a positive, so that would be plus whatever this was, but this is 0, so I don't worry about that. So I'm actually left with my final answer, which is 2 e to the 4th minus 2 e to the 2nd, or e squared, minus ln 2. And that's my final answer, and that's what matches in the book as well. I mean, if you wanted to be, I actually went a step further when I was writing it out. I factored out that 2, so I had 2 times e to the 4th minus e to the 2. But I mean, this is what they actually gave in the back, so that's good enough for them too. Okay, so we did the 25th. Move some papers around here. Okay. Here's the 4th page. We're going to do 33. I think 33 said, for this exercise, find the average value of the given function f over the indicated interval. Okay, so the function that we were given was the integral, or sorry, the function that we needed to do was x squared plus 2x minus 3 over the interval minus 1, comma 2. And what we needed to find was the average value of f at x over the interval. Now for that, we have the formula. It's 1 over b minus a times the integral of the function from over that interval from a to b of f at x and then dx. So in this case, this is our a and this is our b, and there's our function right there, so that our average value is equal to 1 over, so b minus a, so that's 2 minus 1 from minus 1 to 2 . And so again, 2 minus minus 1, that gives me 3. Just copy that out again. Okay, so then we integrate that. So I start with x squared. So when I integrate that, that becomes x, and it goes up by a degree. And then also I have that same number again in the denominator, plus x. This one goes up a degree again, so that goes from 1 to 2, so x squared. And I also have the 2 in the denominator, minus, and this goes up a degree as well, so this was x0, so that goes up to just x. And that's from minus 1 to 2. So now I have 1/3 times plus, I'm just going to clear that 2, so that's just x squared minus 3x, and that's going from minus 1 to 2. And again, I would be very careful about this, because again, I need to subtract this function. So it's this antiderivative at 2 minus this antiderivative at minus 1. So I'm going to calculate it for 2. So substituting in the 2 into that function, minus, so this is at 2, and I need to calculate this for minus 1. So 2 cubed is 8, so 8/3 plus 4, and then I have 3 times 2, which gives me 6. I have a minus here. I'll just put brackets again, just to remind me. I have a minus 3 cubed. If it's a squared, like if I had minus 1 squared, that equals 1. But if I have minus 1 cubed, that's minus 1. So just be careful about that. So it should be a minus 1 over 3. And then I have a minus 1 squared, so that becomes a positive, so plus 1. And then I have minus 3 times minus 1 gives me plus 3. Now I can distribute this negative, so I have minus and minus gives me a positive 1/3, minus 1, and then minus 3. I have 8/3 plus 1/3, that gives me 9/3. I have 4 minus 6, that gives me minus 2, minus 3, minus 6. So we'll write it over a common denominator. 6 times 3 is 18. 9 minus 18 is minus 9 over 3. The 3 goes into the 9 3 times, so I'm just left with minus 3 over 3, or minus 1. And that's what matches at the back of the book, so that's good. All good. Any questions? I don't see any. So if you saw some sort of application of a problem, you know, again, like we did with the interest rate, they said something along the lines of, the interest rate follows this function. Here's our time period, -1 to 2. I don't know, maybe that makes sense in terms of time. And they're able to find an average value for that. So this means that the function 2x plus x squared plus 2x minus 3 over the interval -1 to 2 has an average value of -1. Perfect. So for number 5, yes, okay. Sorry, 45. So we've done 5, 7, 15, 25, 30, 33, and we need to do 45 now. This one required a calculator. And for that one, they said the average body temperature in Fahrenheit in Boston, the temperature in Fahrenheit in Boston over a 12-hour period on a certain December day was given by this formula. So we have a formula. So they told us that the temperature follows this curve, minus 0.05 T cubed plus 0.4 T squared plus 3.8 T plus 5.6. They told us that we're over this interval, the closed interval from 0 to 12. And they said determine so this starts at 6 a.m. Yep. And then the 12 hours would be, this would be like 6 p.m. And what they were asking for was determine the average temperature over the 12-hour period. Okay. So again, we use our formula. And again, our average formula is 1 over b minus a times the integral from a to b of f of x dx. Okay, in this case we're using t, so, but the same thing, same idea. So we don't have to freak out, because you can think of that as d of t. And right here is our a, and here is our b. So again, we can just substitute our values into the formula. So the average temperature is equal to, it's 1 over, and it's 12 minus 0, from 0 to 12, of our function here. So it's minus 0.05 T cubed plus 0.4 T squared plus 3.8 T plus 5.6. And then I almost wrote dx, but it's dt, because that is our variable of integration that we're working over, so we're working with time. And this one, yeah, kind of requires a calculator, but okay, so this one goes up by to the fourth, and I get 0.05 divided by 4 plus t. Now this goes up by a degree, so it's t cubed. So it's 0.4 divided by 3 plus 3.8. I have t. This goes up a degree, so there's 2. And that 2 also goes into the denominator. Plus 1/6 times t. And that's from 0 to 1/2, from 0 to 12. So I'm not going to hide that. I'll bring the calculator over to this side. So again, 0.05 divided by 4 gives me a 0.0, it's negative 0.0125, or that's, yeah, plus. I have the 0.4 divided by 3, which gives me a repeating decimal, so I'm going to switch to 2/15. Yeah, that makes sense. 0.4 divided by 3, not 4 over 3. Okay. Plus 3.8 divided by 2. That's 1.9. Plus 5.6 t from 0 to 12. Now what's nice about this is if I put 0 into each of the individual terms here, it's all 0. So I don't have to worry about the 0 part here. All I'll have to do is just substitute in this 12. So I have minus 0.0125 times 12 to the fourth plus 2/15 times 12 cubed plus 1.9 times 12 squared plus 5.6 times 12. Okay, and again, you could pull out a calculator because it suggests that. Bump. Okay. 0.025, and then 12 to the fourth. Multiply that together, gives me negative 259.2. Then the next one I have is 12 cubed. We'll multiply that by 2 and divide by 15, and that gives me positive 230.4. Then the next thing that I have is the 12 squared, which is 144 times 1.9. So that's 273.6. Add that plus 5.6 times 12 gives me the 67.2. And if I add those all up together, I get 312. Okay, dividing that by 12 gives me 26. So again, that average cold December day in Boston following this curve, the average temperature over that 12-hour period looks like 26 degrees Fahrenheit. And for us Canadians, to give you a reference point, 32 degrees Fahrenheit is freezing. So it's a couple degrees centigrade below zero. So pretty cold. Well, it's not cold, but cold for us. Okay, so we've done that one. Oh, darn. We've hit the 3:29 mark. So I think I'll stop there. That was, I think, some exercises that should help you have nailed down the idea of how to evaluate definite integrals and how we kind of go about doing those things when we have to do substitution. So if there's any questions about that, feel free to send me an email. You know where to reach me at, and I'll try to answer it as soon as possible. These streams will be available still after we're done. You can still watch them again or replay them, and hopefully if you played it through again and you're still stuck, feel free to send me an email as well. Okay, thanks again for sending questions through the chat. It's always good to see that people are using it and people are watching it. So again, thank you very much, and enjoy the rest of your day. Take care.